This is Isaac, and today I'm going to be talking about a case study for the Spencer, Iowa floods that happened this summer, 2024. It's for a class project. It's a research and um, remote sensing project. The goals I sort of got to decide, as well as a little bit of how I was going to approach it. Um, it was a mainly self-guided project with some check-ins along the way. Uh, I wanted to pick the Spencer, Iowa flooding that happened as my study area, and I wanted to see, because I think it's important, because I wanted to see how much the how much the flooding affected Spencer in terms of um, damages to property or property areas, or how much flooding there was, because flood modeling in Iowa is pretty important, because when we do have floods, they can be pretty major. There's been some very historic floods. I remember when I lived in the Quad Cities, my uh, junior prom, I think it was, we looked over the parking lot and it's just all water. Um, but that being said, I just wanted to give my condolences to everybody affected by these floods, um, and I wish you the best. With that being said, I'd like to present the project, and hopefully, um, if not for my understanding, to improve, hopefully maybe this helps somebody else, uh, and we can continue to make better flood modeling and flood mitigation strategies for people everywhere. So, thank you. Here we go. Alrighty. So, this is an image of Okoboji, Lake Okoboji, which is near Spencer, Iowa, and experienced some flooding as well. But let's go. So just some preliminary terms to define in case people aren't aware of some of these things. But you go ahead and take a look. Some key details is that we used ERDOS Imagine for some remote sensing software processing. I used multispectral images on ERDOS and process them on there, as well as doing my classifications that I'll show you in a bit. I used ArcGIS to make my maps, as well as some additional processing for the digital elevation model. And I used Cloud Compare to get some visualizations of that digital elevation model, as well as some nice three-dimensional views of how the topography looks near and around Spencer, Iowa. So some questions I want you to think about as I'm going through this is, how much flooding was there? What areas were affected most? How much area was affected? What types of areas were those? As in, did we lose a lot of agricultural land? Were the buildings affected a lot? Just depending on how you look at this information, you can gather a lot of different details. Um, so the data that I used was from Planetscope, and then I used Earth Explorer to download the SRTM. And if you go back to terms, you can see SRTM is a shuttle radar topography mission. It covered a lot of uh, it covers a lot of area, and it was one giant sample. Excuse me. It was one giant sampling, so it got a lot of information. It's all very even and covers everything similarly. So it's important. It's a common model that people use. So the two times that we took images from Planetscope, multispectral images, was June 10th, because we were trying to get a before and after picture of the flood. The before time is at June 10th because there's a lot of cloud cover or missing dates in between the 10th and the 23rd. And then the 23rd is after the heavy rains that were like the night of the 22nd and the morning of the 23rd. So that was the maximum flood level. So you can see that in these images, where the pre-flood image on the left is fairly normal. You'd kind of expect to see this sort of thing. You can see the smaller channels going out through the floodplain, and then on the right in your post-flood image, you can see the really dark, sediment-rich water from flooding really affecting the area. And the image is much darker because it's a lot more wet. We did have to we did have to do a, by we I mean me, we did have to do a mosaic on the pre-flood image, as the swaths of the satellite did not collect one single image for the area. So we needed to stitch together two pieces. So for the SRTM, we've got different metrics for the pixels. So the Planetscope image was 3 meter by 3 meter pixels, and this one was considered to be 30 meter by 30 meter pixels. And this is the image of the entire area collected by this specific swath of the SRTM image, or the individual cut of that. And then Spencer is that red box in the bottom corner, and you can see the change in elevation in that highlighted cloud compare image in the bottom left. So what we wanted to do was classify the images so that we could figure out the different types of area that were affected in Spencer most by flooding. In order to do that, you have to classify the before and the after image. So we used a couple different classification methods. We tried the minimum distance classification method, which had a lot of assumptions that it made that weren't quite right, even though we used this a piece of processing on Erdos Imagine called the signature editor. Well, it's so essentially you take the areas, as you can see here, these areas of interest in the highlighted parts here, and then these ones are used as the areas that you take together an average for. For this one specifically, it's agricultural land, right? So that would have been done on this post-flood image on the right here, and these areas were selected to say this was agricultural area and applied that as the class. So when doing the minimum distance model or classification, that gave us some different estimates that were incorrect. So we're missing some. If you see the differences between the minimum distance and the maximum likelihood, you can see that minimum distance is a lot less urban area, where in the maximum likelihood it more accurately represents the urban area. I will say that there was some cloud cover that you can see on this image here, for instance there and there, which is going to cause error for the urban classification because we didn't do a fifth classification fifth class for clouds alone, so that'll be grouped in with the urban area, so that'll cause a little bit of error. But besides that, we have forested area, and we have water, urban, and agriculture. Those are the four classes we're going to focus on for this project. We don't need a whole lot more. Clouds might have been nice, but these are the four that I really wanted to look at to see what types of area in Spencer were affected most by the flooding. So, like I said before, the area of interest were trained on through a signature editor to create the classifications on both images. So then through the classifications, we did accuracy testing. It randomly, well, the algorithm on Erdos randomly, quote unquote, picks 50 points, and then I had to make sure the 50 points were within the image bounds, and then I had to go in and manually associate each point with the class that it should be based off of the original image. So the points were assigned to say on each classification image, and then I had the original image underlaid over that, muted the original classification, and associated each point to what the class should be based off of the original image. This gave us accuracy outputs that we can see which classes were the most accurate, and then it takes an overall classification accuracy. So for this pre-flood condition, we can see that the agricultural class, or the agriculture class, had a pretty good accuracy. The forested area had a fairly good accuracy. The water had 100% accuracy, and then the urban was fairly accurate, but because, like I said, those clouds are going to get in the way, it got in the way a little bit. And the overall classification was about 86%, which is pretty good for a non-robust model for this classification. Then for the post-flood, much lower accuracy in different classes compared to before. But part of that is because the soil is very wet. It's hard for the classifier to really accurately assume based off of the signature header, because the agricultural land was greener as it was a little bit later in the season, and so that got in the way with the forested area. And then because the soil was wet and the water was very sedimented, or was full of sediment and very dark, it made that difficult to differentiate sometimes. So a lot of those spots in the lower and higher parts of the image, or the more northern, the more southern parts of the image, they're very dark, and there was sitting water there. But those aren't necessarily part of the flooding, but that's not what the classifier takes into consideration. It's just, is there standing water, which we'll talk about later. So then, using these two images, we can isolate each class in terms of the pixels that are present, and we can analyze the change in the area within the area of interest, within the bounds of the city of Spencer. And we saw that the greatest area changes were within water and forested area. So a lot of that forested area became flooded, right? So that's when water gained it gained 10% of the entire area of interest. So it changed very drastically, gaining 80 or almost 88 million square feet. And then urban and forested areas lost a lot of area. Essentially, this means a lot of urban areas were flooded, a lot of forested areas were flooded, and the water that flooded was what caused that. So if you were a realtor, you could take this urban information, or if you're an insurance agent or somebody, or trying to be a researcher in mitigating flood control and a lot of flooding and flood modeling, we could see that the urban area was pretty greatly affected in this flood. So digital elevation models can be used to help us create a volume estimation of the image. So essentially, it can't be what the flow rate was without like a gauge station somewhere along the line. And so what we did instead is take a current state sitting water estimation, as in the water's just sitting there in this image, essentially because we can't tell if it's moving. So what's that volume in that image? So the digital elevation model is kind of showing the differences in the elevations around Spencer, Iowa. So you can see where a lot of the urban areas it's higher, but there is some stuff towards the south that's a lot darker, meaning it's a lot lower in elevation, so it's going to become more flooded. And then the contour just kind of shows you the generalized change, so where the highest points are and where the lowest points are. So this is overlaid the digital elevation model. It's one of the most important graphs or maps of this entire project, because we can see just how drastic the flooding was from the regular channel flow through the forested areas or through the floodplain to how saturated and how inundated the area became during this time. So that just really emphasizes how much change there was. Then we can see, based off of where the areas were affected, in the highlighted digital elevation model is placed over the original image and the classified image to just show you where the deepest parts were that became flooded. And this image kind of shows us an output of the count of pixels in the post-flood digital elevation clip of the water, and where the regular where the average is roughly what we assume to be the water level. So the surface water, where was that in terms of elevation, and then everything below that would be considered flood. Now, I know this looks like we're ignoring some areas that were still full of water at higher elevations, but like I was saying before, some of these higher areas here aren't actually part of the flooding. I mean, they are flooded, but that might be from heavy rains, and it's not part of the main channel, which is what I was really trying to look at. So, future processing might be done to better estimate total flooding, but this was just to get a general volume of the main channel. So this is the SRTM output of just the water extents of the post-flood image. And you can see on this northernmost part and the southernmost part is what I was talking about before, where these higher elevations that are more yellow or red are not necessarily at the same elevation as the rest of this water level, so I didn't want to include them in the main channel flooding. And then calculating that volume, we've got 14 million cubic meters of water, or if you prefer Olympic-sized swimming pools, 5,647. So, just some visualizations that are helpful to understand this. We can see from this southwest top-down and across view that we've got this blue water level of where we assumed the surface level of the water to be, and all of these elevations here are where those points that we use in the digital elevation model to assume depths were created. So this blue level and below is the volume, and then above was ignored as it might not be considered flooding in these more northern and more southern areas. And you can see that here on this right side of the image, how this main channel is within the floodplain, and then the other points are somewhat outside of it. And you can also see that here, taking into consideration that these three-dimensional views are exaggerated elevations. The scale is not actually 1-to-1 because it would look very flat, but this gives you a visualization of just how the changes in the elevations depending on where they are. So that main channel is really within the deepest part of the digital elevation, or in the deepest part of that floodplain. So yes, using Clay County, their online floodplain maps, we can see that the channel or the flooding that we determined was within mostly the shaded hazard area, as well as filling the blue flood extents, which were there's only one more area that's delineated as possible flooding. So it's a pretty major flood event, right? So there's a lot of flooding within those blue extents, and we can see that we also saw that with our flood classification. So it's good to know that some of our methods match what professionals have been using. So some main takeaways or key points: that we saw a large amount of flooding, a huge volume, 14 million cubic meters of water that were flooded. The areas that were affected the most were the forested and urban areas. And some of the most important things to know is that almost 40 million square feet of urban areas were affected, destroyed, flooded, however you want to look at it, but that is a significant amount of property damage. And then the inundated areas, so whether that was the pre-flood image where it was the river or it became the flooded area, increased from 2 to over 12% of the whole area of interest. And because we double-checked our work, we can see that the 2024 floods were a hazard to the community, and there was extensive flooding by the Clay County standards. So feel free to email me if you have any questions, or if you want to know some more about this project, or if you want to put it in the comments, anything. If you think it's really interesting, or you want to see more things like this, let me know. But yeah, I thought this was a very interesting project to do. I think it's a very important area to research, and I'd like to do some more things like this. But I thought that this project was a pretty good capstone for what I've been learning in my class about satellite imaging and processing images. So thank you for watching and paying attention. Let me know if you thought this was helpful in any way. So thank you.